Also, sich der Titel nochmal geändert. Multi-gigabit Networking Demands Complete Optical Communication Systems. Die wird gehalten von dem Herrn Juergen Schachtschneider und von César Esteban. Ja, die beiden Vortragenden sind im Bordnetzbereich ja auch keine Unbekannten. Sie haben mir ihr System schon vor einiger Zeit schon vorgestellt und haben das in der Zwischenzeit weiterentwickelt. Und da sind wir mal gespannt, was Ihr System heute kann.
Ja, okay, danke. Dann bitte. Fangen wir mal an. Ja, schönen guten Tag an die Teilnehmer. Wir freuen uns auf das Interesse. Just one point. I will start with a short introduction of the company, and then I will face over to my colleague César Esteban, who's sitting in Madrid. And César is our technical guru. He will guide you through the presentation itself about multi-gigabit stuff. That's correct. Last year, we have already made a presentation about the 1 gigabit, and today we gave at that time a little bit indication that we are working on multi-gigabit. So out of this one today, multi-gigabit will be the subject. Looking to the next file, we have an agenda. César, can you switch, please? Yeah. So executive summary. Here I just, wir können das in Deutsch machen. César, sorry, I make this part in German. Im Grunde genommen eine kurze Überblick über das Firma an sich. Wir haben also in einer gewissen Form ein Alleinstellungsmerkmal. Wir sind in dem Bereich Gigabit Ethernet tätig, und zwar dort nicht im Kupfer, sondern in dem optischen Bereich, also Polymer oder Plastic Optical Fiber. Die Technologie, so wie sie momentan auf dem Markt verfügbar ist, ist also einmalig. Es gibt also keinen anderen, der von der Geschwindigkeit, Distanz und dann auch von den Kosten vor allen Dingen ein System anbietet. Zumal wir am BFR, also Bit Time, Bit Failure Rate, about 10 hoch minus 12 haben. Das heißt, das ist ganz wichtig für die für die Use Cases. Automotive, klipp und klar, ist Number One bei uns. Und wenn Sie Ethernet Backbone sehen, Smart Antenne ADAS, das sind alles Dinge, wenn da 1, 2, 3 Bits umkippen, das kann horrende Folgen haben, die nicht so angenehm sind für die, die entsprechend dabei sind. Das andere ist der Bereich EMC-Compliance. Und das ist ein Punkt, die Industrie hat jetzt gelernt bei den 100 Megabit, die jetzt im Einsatz sind. Alles, was im Labor einwandfrei gelaufen ist, in dem Moment, wo es ins Auto hineinkommt, wird es schwierig. Denn das Auto ist nichts anderes als ein, verrücktes EMC-Gerät, wo alle möglichen Störspannungen reinkommen. Und diese optischen Kabel bieten die Vorteile, dass praktisch hier keine EMC-Störungen mehr reinkommen. Das heißt, durch die optische Kabel ist natürlich das elektrisch aufgehoben dabei. So, let's switch to the next file, please, César. Ganz kurz, Business at a glance, also 2010 wurde die Firma gegründet. Bis vor einer Woche hatten wir 28 Mitarbeiter, inzwischen sind 2 dazugekommen, sind 30. Wir sind ein Fabless, das heißt also reines Designhaus. Wir lassen die Sachen, wie fast jeder in dem Markt, bei TSMC in Taiwan sprechen und produzieren, um da auch den Scaling-Effekt mitzunehmen. Wichtig bei einer neuen Technologie ist ja, dass man auch bei den Association dabei ist, also bei JASPA für den japanischen Bereich, Open Alliance, auch bei den Standards, wobei KDPOF aktiv beim IEEE in dem optischen Standard jetzt arbeitet. Das heißt, unser CTO hat den Share dort. Und der andere Bereich ist die Kunden. Das heißt, wir sind also mit dem Produkt schon seit über 2 Jahren beim 1 Gigabit in Produktion. Und beliefern über ein First Tier, jetzt darf ich keine Werbung machen, einen bekannten schwäbischen Autohersteller. Wichtige Information dabei ist also die gesamten Qualifikationssachen, IEEE und diese Dinge, die dazugehören, um bei einem Autohersteller entsprechend in die Liste reinzukommen, um auch die Produkte liefern zu können. Das haben wir alles schon gemacht. Das heißt, in der Form sind wir gut aufgestellt. Next, please. Wichtig sind noch, wo wir vertreten sind. Das Headquarter ist in Madrid, das ist auch César. Wir sind in Frankreich und in Valencia vertreten. Wichtig sind die Commercial Offices, die sind da eigentlich, wo der Markt ist, die Kunden sich entsprechend bewegen. Das ist in Schweden, das ist obvious. Deutschland, ganz klar, da ist mein Verantwortungsbereich. Dann haben wir Kollegen in Japan, die den japanischen Markt betreuen, Korea und ich selbst bin noch verantwortlich für China. Das kommt aber aus meiner Historie heraus, dass ich über 20 Jahre in China rumgereist bin. Wobei ich hier eine kleine Bemerkung machen möchte, die Chinesen, was wir hier in Europa in 2 Jahren brauchen, machen die in 6 bis 8 Monaten. Das heißt also, bei denen ist Speed all about, wie es so schön heißt. Die Botschaft hier ist ganz einfach, egal wo sich ein KOM oder First Tier bewegt, wir sind da, wir können in diesem Bereich überall den Support stellen. Ja, Fragen jederzeit. Am Ende der Präsentation sind auch unsere E-Mail-Adressen angegeben, da freuen wir uns über jedes Feedback. Damit würde ich den Bereich kurz schließen. And César, it's now your turn.
Hello, everybody. Now I'm explaining the optical multi-gigabit technology that KDPOF has been developing for more than 2 years. So as you can see here, the auto display roadmap and data rates for automotive, for cameras and sensors are growing, not only the display size, but also the resolution, okay? And also, if we have this tendency together with also the applications are using uncompressed data transmission, then we get that between 2020 and 2022, we will be, or we are using cameras and sensors transmitting 2K or 4K video formats. That means you can see on the right column that the bit rates that are required, most of them are above in fact, all of them are above 1 gigabit per second, and the multi-gigabit technology is required, okay? So there are basically two options to go for electrical technologies or for optical. It is well established in the industry that there is a theoretical threshold that is the 100 gigabit per second by meter, that it separates those applications where copper makes sense and those ones close to this threshold and above it where optical make full sense in terms of features, cost, power consumption, and so on. So as we are moving from 2K to 4K in the video cameras, as an example of application, we see that the solution should move to optical. Otherwise, there will not be economical feasibility for copper harness solutions. So here is how the electrical technologies are approaching the issue of upgrading the bit rate. Basically, they are adding more parallel lanes, which add cost and weight. They increase the connection size, and they decrease the mechanical flexibility. Together with this, they are using larger conductors with shielding, which also increase the weight and the size of the cables and connectors, and decrease the mechanical flexibility also here. Together with this, they are also increasing the digital signal processing complexity, which means that we will have a higher power consumption and an increased latency. Together with this, we will have also a higher signal amplitude, which impacts on the power consumption, and also there will be higher or more EMC issues. On the other hand, when we are talking about optical, we have a cost-effective reach with the flexibility to locate high data rate components in optimal locations. We will have a cable size, flexibility, and connector size that have increased mechanical flexibility of the harness and easier installation and routing of the cables. We will have a lighter solution, which impacts on the fuel efficiency, and it will be an upgrade path for higher bit rates demands in the future. The glass fiber does not work hardened. That means that fiber cables can resist repeated bend and vibration without breakage, and they are performing even better than copper. And there will be reduced EMC issues as glass fiber provides galvanic isolation, EMI resistance, and at the end, this results in a reduced engineering costs. There will be a lower power consumption compared to copper solutions that impacts on the better battery life and improved thermal management. And finally, the link reliability will have reduced risk of interconnects loss failure because of the aging of the cable and the shielding. So glass optical fiber communications have been used in harsh environment applications for years. So the technology is there. There's only the need to leverage all these technologies to automotive. So the 4 key components here are the transceiver, the fiber, the cable, and the connectors. So I will explain you briefly the technology in multi-gig for optical transceivers from KDPOF. So the functional characteristics of the transceivers will be according to IEEE standard, the 802.3ZZ, which is now under development, led by KDPOF. The speeds will be from 2.5 up to 50 gigabit per second at different generations and at different steps. The length, the target length is 40 meters with 4 inline connectors, okay? And for 50 gigabit per second, only 2 inline connectors will be in the spec. So the key automotive characteristics compared to existing technology for data centers, that is the XG-based SR, is a wider operating ambient temperature in operation that will be from -40 up to 105 Celsius degree. And the reliability will require 15 years of operation with less than 10 failure in time fit. There are some open topics that I'll explain later, such as the VCSEL reliability, the higher insertion loss channel, the higher optical return loss channel, the low cost and low power consumption requirements, the necessary great EMC compliance, and also some requirements such as the OEM side channel for dependability. So the leveraging of mature components developed for datacom market applies to the infrared VCSEL and photodiodes, the OM3 multimode glass fiber, with huge economy of scale in other markets, and cable structures already used in harsh environment applications. So we are also implementing an adaptive communication system with advanced digital signal processing that will be designed for compensation of impairments caused by large parametric deviation, which will result in a high production yield, and at the end it will be a reduction in the cost. So the sensitivity improvement to support much higher insertion losses, and the automotive quality proven and high volume CMOS submicron technology nodes, okay, that will also impact on a reduction in the cost. So the VCSEL is the least reliable element compared to the CMOS IC and the PIN photodiode. The VCSEL lifetime decreases with current and temperature increase. About the temperature, we cannot do anything because the restrictions of automotive establish that it should be in operation between -40 and 105 Celsius degrees. That means that we have to play with the current. So the current density has to be reduced to achieve good reliability at junction temperatures of the chip of 125 Celsius degree. That impacts negatively in the performance of the communication system as the bandwidth is reduced, the noise is increased, and the optical power is also decreased. So we have to apply digital signal processing to counteract all these factors. Additionally, the VCSEL process variation is big. Oxide aperture area can vary from -40 up to +60%, which means that different lots will have different current densities, different bandwidths, different noise, and different optical power. So KDPOF has to develop adaptive electronics to allow all these variations in the process. Here you see in the figure how the temperature and the current impacts on the time to failure. Okay, as we move upper and in the right, we will have a better performance. Okay, and as we move to the left, we will have higher temperatures, and we see how the reliability decreases. Okay, we see 3 different lines corresponding to 3 different the current densities. And you see clearly here that the lower the current density, the higher the reliability. So we have to play with low current densities to support high temperatures with a good reliability, at least the reliability that is required by the automotive market. Here we see the investigation we have done on the wavelength of the VCSEL, and we have concluded that as we move to higher wavelengths, around 980 nanometer, we have the optimum wavelength to operate such in that automotive under automotive requirements. Okay. As the presenter said before, we will share the presentation after this conference, so you can go into detail and you can contact us if you have any comment or any question. Here you see the on the left 50 gigabit per second communication on PAM4 coding line. You see on the left the blue diagram is the reception after 40 meters of fiber, and on the pink screenshot is the same, but after applying the KDPOF receiver. Okay, with advanced digital signal processing, with the clock and data recovery and equalization. You can see how the eye diagram is open in a big deal. Okay. And you can see the same repeated at 105 Celsius degrees, because this one is at 25 Celsius degree. You see, as the temperature increases and moving between the two temperatures, the situation gets worse. Okay. So the channel is standardized under ISO. You see the references on this slide, and we are targeting at least 40 meters with 4 inline connectors at the operation temperature that I mentioned before, with aging temperature at this from -40 up to 125 Celsius degree. The installation temperature is from 10 to 30 Celsius degree, and it must support or withstand mechanical loads, chemical loads, flame resistance, well, all the Kejiri criteria for protecting the connector, and so on. The channel, we are investigating the optimal fiber, and our conclusion is close, and we are targeting to the OM3 laser optimized fiber, multimode glass optical fiber with 50 micron of core diameter, because this is also the highest volume today in the market, and we are benefiting from a huge economy of scale. Okay. Here is the transceiver concept we are developing in KDPOF. You can see here that is a single component transceiver that has 2 holes. One is for transmission, that is aligned with the internal VCSEL, and the other one is the reception hole that is aligned with the photodiode. Okay, it's a single CMOS die with a SerDes interface, the physical coding sublayer, the physical medium attachment, and the physical medium dependent sublayers, NDIO management interface, all the digital signal processing, the analog front end, the VCSEL driver, and the transimpedance amplifier. All this is integrated in the CMOS die, and the CMOS die is also integrated with a single component with all the photonics, the VCSEL and the photodiode, and all the optics, which at the end is the lenses that bend the light 90 degrees, and they collimate the light to focus it into the fiber. So the assembly by the tier 1 will be just soldering the component onto the PCB via a reflow soldering process, the same as any other IC. And afterwards, the tier 1 will mount the connector housing on top with a kind of click film, okay, mechanism that it does not need any reflow. The connector housing will be provided by connector and harness manufacturer. So the connector is just a push and click mechanism. There are 2 options for the header or the mid-board connector. The edge header connector has the advantages that it requires less components, fewer components, and fewer steps in the ECU assembly process. On the other hand, the mid-board connector, which is located in the middle of the PCB, has a higher flexibility for positioning the integrated circuit on the PCB without any layout restriction. So there will be an optical pigtail, you can see in yellow color, attached to the connector to drive the light to the ECU front panel passive connector. So no high-speed traces will be throughout the PCB. There will be very short high-speed traces, which will simplify the EMC compliance, and the mechanical requirements will be easier to meet. So both options are available. The header connector or the mid-board connector with optical pigtails must support automotive requirements, as I stated before, in terms of temperature, reliability, mechanical and chemical loads, and so on. And for the mid-board connector specifically, there will be the optical pigtails that will require to comply with the mechanical requirements and that are much less restringent than the other case. The cost must be low, and there must be a good optical connectivity. It does not need any electromagnetic shielding, since it is already integrated inside the KDPOF transceiver. Okay. Regarding the fiber, the plug connector and the inline connectors, they must support the same requirements as the header connector, and it must be also low cost, and it should support inline connectors that must have a small size. All this must be developed in parallel with the technology to go to the market and to be in the start of production in parallel with the fibers, connectors, and so on, together with the transceiver. So this is a detailed table that compares parameters between optical on the left column and copper in the right one. So you can see regarding channel insertion loss, equalization complexity, echo cancelling complexity, forward error correction, and so on for both technologies, optical and copper. And you can easily understand the benefits of optical and copper for different use cases. So I will not go in detail with this because you will have this presentation. So I'll pass quickly. As I said before, if you have any question on this, do not hesitate to contact us. And let's move to the glass optical fiber robustness. Here you can see the fiber we are using under test. That is a Sumitomo all-glass multimode fiber with 50 micron diameter. And it uses a technology that is not new in the industry, which is the bending sensitive fiber, which adds a kind of notch at the cladding, just in the interface between the node and the core and the cladding. And this notch prevents some optical modes from leaving the core of the fiber, and they go back into the core, and it supports aggressive bending much better than traditional fiber. Okay. So on the bottom side, we have the test setup we have used for most of the tests that I'll explain you later. Okay. That this is, for example, the Sumitomo performance in terms of connection loss. Here on the left side, you have the number of connection and disconnections and the loss increase after these connections. You can see that there is no significant increase in the loss. And on the right side, you have a similar test, but taking into consideration the temperature. Okay, as you see, the temperature effect is very reduced in terms of connection loss. Here is the loss budget for 50 meter. You can see we are using a 3 sigma insertion loss for the inline connectors. Okay, for 1, 2, 3, and 4 inline connectors. We are adding also the connection, the loss of the 50 meters of the fiber, and also the aging margin for the fiber. So at the end, on the last row, we have the total insertion loss for 15 meters of glass optical fiber for 1, 2, 3, and 4 inline connectors with 50 meters, taking into consideration also aging, and we are repeating the same calculation for 50 meters, okay, where we see that the total loss is increased a little bit for the 4 cases. Here we have the performance in terms of macro bending. dynamic bending, and you can see on the picture below how after applying 1 million of cycles, the optical fiber is perfect, and after 10,000 cycles, just 10,000, the shielding of the copper cable is clearly damaged. Another test has been applied, applying no bend, 25 millimeter bending radius, 15, 7.5, and no bending. And you see on the left side how the insertion, the loss is increased, and we can see in the blue and brown curves that there is no significant increase in the loss compared to conventional fiber, where there is an increase when we are applying the 7.5 millimeters bending. Here there is another test made with a specific graded index hardcore silica fiber, which is a mix of plastic and glass optical fiber. And we see on the right side, as we increase the number of 2 millimeters bending radius turns, there is an increase in the insertion loss, but it's very reduced and very, very bounded. This is a microbending test, so applying 36 kilogram to the specification that is standardized, and we see that no effect at all is on the optical power received at the other end of the fiber, so there's no impact at all. This is another slide that represents the bending sensitive fiber technology that it will be used for automotive fiber. And this is the vibration test with in the 4x, okay, random vibration. And at the end, we have the water resistivity result, okay, that when we apply over this connector the water, there is no significant change in the loss, okay. We have also done other tests like type band stress. With these results you can see here, so compared with conventional fiber, there is significant improvement, and also the seat stress test, okay. So this is the standardization group where all the harness and connectors are standardized. And this is just to finish the timeline we are having in the IEEE standardization group. Okay, you can see that the standard will be released around 2023. Engineering samples will be available in the third quarter of 2022, and the start of production will be in the third quarter of 2025. Thank you very much for your time.
Okay, ja, vielen Dank für den Vortrag. Ja, gibt es Fragen aus dem Auditorium? Ich frage mal in der Zwischenzeit, falls jemand noch was schreiben möchte. Ja, das ist jetzt ein optisches System. In der Parallelsession und in der Keynote haben wir gehört, man arbeitet daran, den Bordnetz, die Herstellung und die Montage des Bordnetzes zu automatisieren und dann eventuell ganz neue Architekturen zu entwerfen. Da sind jetzt überall Leute dabei, die mit Kupfer arbeiten.
Okay,
ja.
Maybe a little bit in English because César speaks Spanish, French.
Okay.
Yeah.
Sorry for this. In the parallel session and in the keynote, there is work and discussions about the automation from the Bordnetz harness, and in this working groups are, I think, mostly or only people which working with copper lines. How can the optical transmission be part of the new Bordnetz?
Okay. We make it simple. You can use the optical fiber similar like the copper ones. There's no difference. You can have the bendings, therefore the bending tests are very important for this one. Then also stress test, something like this. And we have also some experience with some harness providers who confirmed that is usable like in copper. The next point is about the weight, not to forget, because, you know, we all are CO2 branded in a certain extent for this one. So that means the weight of this cable is much, much lower than the copper ones to be seen. And the next part, when you're coming to 5 gigabit, 10, 50, 25 gigabit, you must have a certain connector. And the connector has a size, has a weight, and then the form factors in the car OEM that itself It's quite limited what you can use for this one. So these are the benefits in the moment from the mechanical stuff, but not forget the benefit for the electrical stuff, because whenever you have copper, and I have to say the car industry had a lot of experience with now the 100 megabit and also starting with 1 gigabit in copper. They notice EMC is something which we as engineers always can solve, but the costs are sometimes very huge in these cases. And here we, with our EMC compliance, what we have, that means no EMC influence, even up to the chip level for this one. We have a big, big advantage. So there are two things. One is comparable with copper, no restriction, also from the temperature, as you have seen, copper temperature, automotive ones, and the POF and the glass sole, it is the same ones. The benefits are CO2, the weight, and the form factor. So we're looking more forward to discuss with, let me say, first tiers or with these automated companies who are doing this one. So we are feeling very, very comfortable. On the other hand, we have to say this type of technology is heavily used in two things. One is the military stuff, and the other is the server rooms you have, the big, big server farms, I have to say. So it means when you have the approval in these both areas to be extremely reliable for this one, automotive seems to be then more issues coming on the table as a challenge, because optical is something for an electronic engineer, which is a little bit, how to measure things for this time. And what we noticed for these cases is that whenever you discuss in depth about the technology itself, we have, with all respect, to make people aware, yes, of course, it's optical, and here are all the benefits. And you can't measure it on one hand with your voltmeter, whatever type of stuff. But once you have it in the card itself, you will recognize, especially in the practice case. Laboratory is one thing, practical in the car is another one. So from this point of view, we have, in the meantime, convinced a lot of people to listen to the optical ones. But there's also parts to say, it will not replace the copper ones, because this is very, very important. You have low speed CAN, you have FD CAN, whatever type of stuff, which means up to 1 gigabit that will coexist. And above 1 gigabit will be also maybe a type of coexist for this one. But once you're coming to the 25 gigabit or 50 gigabit, then it's the question about reliability. As I said in my starting point, bit failure rate, 10 exponent minus 12. This is something which we can guarantee in this type of technology. And when you go ADAS level 4, level 5, you want to be sure that the car is driving along the street and not in the ether.
Okay.
So it was a little bit longer, but you see, this is, I'm fully aware about this problem. And this is 80% of the discussions I have in the development area is about the concern about optical stuff. And some of them, they have history with MOST. It was at that time a fantastic product. So, and when you talk to senior gentlemen, which are now in the decision position technology-wise for this, of course, this is then coming back, and they remember all the challenges they have had 20 years ago with the MOS stuff.
Okay, good. Thank you for the answer. Now we have a lunch break, and we will continue with our sessions on 13:15. Yes, um 13:15 Uhr geht es also weiter, und bis dahin guten Appetit und dann bis nachher wieder.